Okay, let's do an equilibrium problem here. Got a beam attached to a wall and a wire, and we want to use equilibrium to be able to solve for whatever variables we want. So our starting point is draw the forces. We need to draw a force diagram, but we need to not only draw the forces and what direction they're acting, but also where they're acting from. So we have gravity, which is pulling down, and gravity, so technically speaking, it always pulls from the center of gravity, which almost always coincides with the center of mass. Yes, those are different things, but we don't need to get into the details of either one really. The center of mass often, but not always, coincides with the geometric center. When you're doing problems, unless you are told where the center of mass is or how to figure out the center of mass, you can just assume that the center of mass coincides with the geometric center. And so that's what we'll do here. So this is gravity, Fg. And of course we have tension. So we have tension going there. And over here, we're also going to have a force from the wall. The wall itself is going to be exerting a force. Now, to keep this in equilibrium, tension has an x component, gravity doesn't. And so its x component is to the left. So the wall has to have an x component to the right to cancel that out. That's clearly got to be true. And you can also hopefully see that this is also going to have to be upward, just based on the configuration here. I'll show you later how I know that. So I'm going to have a wall force that's going up and to the right. And I'm just going to call this Fw. Now, this force might be a normal force. It might be a combination of normal force and static friction. I don't know. I don't need to know. I just know there has to be something acting there. So let's set up Newton's second law. So we'll start with the x direction. We've got two forces that have an x component. We've got Fwx plus Ftx. That has to equal 0. Now this Fwx, I don't know right now, I don't know anything about it. So I'm just going to keep it as Fwx, but tension, I can clearly get the x component of tension. If I do a vector diagram here, here's my triangle. Okay. This is Ft. That's the angle theta. I know this down here is Ftx, technically the absolute value of it. Okay, so that means that's the adjacent side. This is going to be minus because it's going to the left. So this is minus Ft. Adjacent means cosine. Okay. And that has to equal 0. We also need to do the y components. This is Fwy plus Fty, and I already know what the y component of gravity is. It's going to be minus Fg, so I'll just put that in as minus Fg equals 0. And again, we can do a little vector analysis. That's Ft sine theta. That's minus Fg. That has to equal 0. Okay. You'll notice, although I did vector analysis for the tension, I didn't do it for the wall. That's because I don't have an angle. I haven't been forced to define an angle, so I didn't worry about it. But certainly if I wanted to write an angle down, I could do that as needed. Now let's do torque equations, because when you're doing these equilibrium problems, you're going to have to set up a torque equation. The sum of the torques about your rotational axis has to equal 0. Now it's both good news and it's just really neat. When it comes to equilibrium, there is, like in this case, this is static equilibrium, so there is no rotation. There's no obvious rotational axis. So we get to pick wherever we want to be the rotational axis. So, and that makes the problem actually easier to solve. It turns out the best places to choose are where your forces are acting. So here would be a good one, or here, or here. We have three excellent choices. And so I'm actually going to set up all three torque equations. So I've got to set sum of the torques. I'm going to do sum of the torques, and I'm doing it at, I'm going to start with at FW. This is my own personal notation, just lets me know I'm doing torques now, and my rotational axis is right here at FW. So FW is not going to create a torque because it is being applied right at my rotational axis. So its lever is 0. That means it doesn't create a torque. So these are the only two forces creating a torque. So I'm going to have the torque due to tension. And it's obviously got to be minus the torque due to gravity. This has to equal 0. The torque due to tension. So for torque, our formula is the force. So in this case, that's tension, of course. Ft times the lever. Okay, well, let's just call this whole distance right there. I'll call that R sub t. Oh. So this will be R sub t, and this will be the sine of theta. I'll move this torque over to the other side. So then I'm going to take Fg, and since it's pulling from the center, I can say that this distance from here to where Fg is acting is half the length of the board. So I'll just say L over 2 is its lever arm. And then I would also have a sine, but it'd be the sine, my lever arm is horizontal, the force is vertical. It'd be the sine of 90. Sine of 90 is, of course, 1. So there's my first torque equation. All right, let's set up another one. Sum of the torque, let's do at Fg. I'm just going to move down the line here. Okay. So if this is my rotational axis, now Fg is not going to create a torque because, again, its lever would be 0. It's acting right at the rotational axis. So only Fw and Ft are creating torques. So I've got the torque due to the wall force minus the torque due to tension. Has to equal 0. Okay, so the wall force, that's going to be Fw. Now it's acting L over 2 away from the rotational axis. And I've got to have an angle here. I've got to have the sine of some angle. So let's see, the lever arm is horizontal. So I'll draw that, and I'm going to do this, and I will just call this angle, I'll just call it alpha. Sine of alpha. Okay. Move this torque to the other side. Torque due to tension, that's going to be Ft. Now, Ft is actually acting, how far away is it from Fg? Well, it's this distance right here. So I'm going to run out of space. So let me do this. Erase that and write this on the next line. This all has to equal Ft, and its lever arm is RT minus L over 2. That's how I get the distance from here to here. Take RT, subtract L over 2, that'll give me that distance. And then I still have the sine of theta because that's the angle between the lever arm and the force. So that's my second torque formula. And here's my third. This is at Ft. Okay, so now Ft isn't creating a torque, only these two are creating a torque. So that's the torque due to the wall minus the torque due to gravity. That has to equal 0. Okay, the wall, so this is the force of the wall. It's how far away from the rotational axis, R sub t. Okay. And what's that angle? Oh, alpha, that's right. It's the angle between the force and the lever arm. or the lever, excuse me. And then we have FG, and it's this tiny distance here, which again is just the RT minus L over 2. There we go. And that's it. Those are the 3 torque equations. So I've actually written down 5 different equations. And you may be wondering, do we actually need all 5? It depends on the problem. It depends on what you know and what you don't know. And you have to go through and look at that. You have to say, well, what do I know? What don't I know? A problem like this, you might know the mass of the beam and theta. That's often all you know in a situation like this. Oh, well, you probably know where the string is attached, or the wire is attached as well. So you know RT, theta, and the mass of the beam, or the weight of the beam as a consequence. And so that's all you would know. You'd be trying to go through and figure out, okay, now what? Well, you also know the length of the beam. That's something else you probably know. So based on those knowns, knowing theta, the length of the beam, R sub t, and effectively the weight, okay, so I know RT, I know theta, I know FG, I know L. I could use this formula to figure out the tension. Once I know the tension, I can easily go through and figure out FWX and FWY. And after I know FWX and FWY, I could get alpha if I was so inclined. But that's the idea. You write down as many formulas as you need. But you have to understand how to set them up. So this is just one example of how to set up your formulas, how to do the force diagram, so that you can get these formulas that allow you to solve for the unknowns.